Okay, finished sending a message, and now put down the volume.
Okay.
Because it was a crazy 14 days and it's not finished yet.
Oh, wow. All right. Well, so good afternoon. Good afternoon, Jan. Yeah, yeah.
Good.
So, yeah, we were just trying to connect with our guest. So we're going to try to resolve some of these technical difficulties and see if we can get him back next week. But yeah, in the meantime, 2 launches on my side, and sounds like there's been some progress on your side as well.
There's no progress on
No
my side.
progress. Oh, okay.
I say okay, no progress, but let's follow the session. Anyway, yeah, there is a little bit progress. I've been going through the course there of what was her name already? Bros, yeah. She's Belgian, by the way. I thought she was from Holland, but she's Belgian.
Nice, excellent.
Okay. Then I saw that there was Matt with his explanation. I say, oh, that's very interesting. So it doesn't matter if I don't have anything. It is more interesting than what I have to say, because it's really something that, yeah, it's the basics of historical modeling,
Yeah,
just
yeah.
in another domain. But let's leave that for his presentation.
Yeah, yeah. I'm looking forward to that. Yeah, I want more people to be thinking in terms of the mathematics of data. So yeah, I'm excited to see his application of CRDTs. So yeah, but the
I saw that in.
oh, maybe we have it fixed. Well, you saw. Yes, we can hear you.
Okay, we're good. Let's see if we get the video, and then we made it all the way.
All right, excellent.
All right.
Woohoo!
We did it. All right.
We did it.
It's always the first meeting of the day, you know, and you use Linux, and you never know what you're in for when you're using the browser. Yeah, so here we are.
Yes, yes. Well, congratulations for getting audio working on Linux. That is...
I know, 2024, the little things, right? Yeah.
Awesome. Awesome. Welcome. Yeah, so should we use your real name or your screen name?
Yeah, you can call me Matt.
Good to meet you, Matt. Yeah.
Welcome, Matt.
Hi there.
Yeah, so we are live on YouTube now.
Great.
Is it good morning, good afternoon, or good evening in your world?
It's good morning. I'm in the Rockies, so it's a nice bright 7 a.m.
Wow, thank you.
I'm glad I got up so early. I would have totally missed the stream.
Oh.
Okay.
Yeah, and I see that you've got some projects going on. Your table looks like you do some hardware.
A little bit of hardware, actually a lot of hardware, and then a lot of like Linux projects, high performance computing, both gaming and server. So yeah, but some of the projects I'm working on, mostly, if you're familiar with Kubernetes, I kind of see it as too large of an ecosystem at this point, or at least the SMB case, and I work with SMBs. So I've been doing a lot with virtualization, and particularly disk images, right? So I love the concept of a container, but I don't like is it's not quite isolated the way I'd want, right? I want every time this thing boots up, I want it to have like the same virtual CPU. I want it to have the same hardware. You don't really get that on things like Docker or Podman. You get close, right? It's great as long as you don't try to like go too off the reservation, like maybe changing CPU vendors, going several generations around on the CPU. Things will typically work. And that's why it's really successful kind of on the data center side, is because you've got that, typically it's a server chip and they're within a couple generations of each other. So the support's pretty good. So I work more with like QEMU and kernel virtualization. So one of the features, I think it was maybe a couple of years ago, that was added to QEMU is around the disk images, particularly QCOW2. You basically have the ability to create a image from an existing image, and it just tracks like the block level device changes.
Yeah.
And so what I've done is I basically just have written a Python front end for QEMU where I can boot my virtual machine. You know, I can apply some devices. I don't do a ton of devices. I'd like to add GPUs, but that's a whole nother conversation. But I boot the thing, I can boot it with a CD, install my operating system, and all the changes to that disk, I'm actually just storing in RAM until I'm like done with that virtual machine and I tell it to shut down. And then the last thing it asks me is, do I want to save?
Yeah.
Right. So it's kind of clever because basically you could do anything during that. Like you could install whatever you want. You could update a whole bunch of dependencies. You could check your code and make sure it works, or if it doesn't, you can just blow it away. Right.
Yeah.
So that's typically now how I just develop all my workflow. And then when I go to push the thing to production, I can pass through, I think it's called Plan 9 file system. I can pass through basically a directory that shows up in the guest. And then I basically have a script in that guest that's looking for a startup. Like it's looking for a file with some commands in it. If it finds it, it'll run them and then shut down. If it doesn't, it just boots into the desktop. So yeah, I schedule things, load it, shut down. And basically every time it runs, it's like the last time it ran.
Yeah. Yeah. I like that.
Because the only thing that changes is the code.
Yeah.
And you could even make that read only if you want. But basically now it's like, okay, just a folder structure. I've got my image, I've got my code, and then I have a command to just repeatedly run it. However often I need to.
Yeah. So
right?
when you save, is that similar to Docker layers, where it saves a layer to go on top of the?
Not quite, because it's dealing with block storage.
Okay.
I think you could get there. I'm not sure how to get to there from here. Because when you're booting a whole operating system, right, it typically expects to be on a block device.
Yeah.
Right. So just a little bit different layer of doing it. But yeah, I have some pretty beefy workstations, and I'll just boot them up. And then literally all the changes, so all the changes to the disk, and then all the network activity. So all the packets, I'm capturing those as well to a file.
Interesting.
And then when I shut that thing down, it actually analyzes the whole like capture and shows me all the places I connected to.
Yeah. So you use that for risk mitigation,
Forensics, basically.
Yeah.
Yeah,
Nice.
exactly. So it's like if I notice like, wow, this process used to only connect to these places, and now it's connecting all these other places, I kind of know something's up. Yeah.
Yeah.
So
That is
and
pretty cool.
then because basically I'm using a lot of Python, right? And I kind of view every extra library I install as just more risk surface.
Yeah. Yeah.
Both for
have to be
it
suspicious.
not being supported in the future,
Yeah.
or
There is
just
that.
having a vulnerability that I just don't know about. So if you're familiar with Apache Airflow,
I'm afraid I'm not.
It's a pretty popular open source like scheduling DAG kind of execution framework where you can say, hey, like I need to run these tasks. They're kind of complicated and I need them run in certain order. I've basically written really lightweight replacements for Apache Airflow, both the scheduling component and then kind of that DAG component.
Okay.
They use basically minimal libraries, right? Because I don't want to, if I pick up and move the virtual machine in the code, I don't want to install a bunch of stuff to run it in a new place. So I've got two applications that basically just do that. They take like a JSON file as an input to say like, here's my tasks, here's how often I want to run them. And then the other one is that kind of that DAG where it's like, okay, I've got 6 tasks. I need these 2 to run first, and then this one depends on these 2, and then this one after
Yes.
that, all that sort of stuff. So between the 2, I can schedule the tasks, and then I can coordinate those tasks.
Yeah. So you wait for all of its dependencies to finish before you can then start the next one.
Yeah, so I do that, and then I basically can pass, like, because I can access the file or the local system with the virtual machine, right? Or a network resource or whatever. I can, have like one virtual machine that's like Windows or a version of Linux or something, do something with some data immutably, right? Because it may be touching files, but it doesn't necessarily save any of those.
Yeah.
Get the output, and then take that as the input to the next one, which could be a totally different operating system, right? Do some processing there, and you can have some very complicated workflows, and you're not too worried about repeatability because every time you boot it, it's like the first time you installed everything.
Yeah.
Yeah.
That is a really cool system. And what are you using this this infrastructure for?
So I'm in the kind of the business system space. So I don't necessarily like write an ERP or like an enterprise management systems, but I interact with them, right? And it's like those are typically slow, boring, not fast moving pieces of software. And what really counts is like, when you go to close the books, can you reliably realize that everything did what it was supposed to do for like quarters on end, right? Where I might not want an update, and I might want to check that update well before like I run multiple months to find out, hey, there's some bug in some like pandas or something that's messing something up, or some other library, right? So a lot of that, a lot of kind of moving data around. And an added bonus to this is I don't store any of that data.
Yeah.
Right. So it's like I get rid of any of those privacy concerns of like, I'm really just, I wake up, I go get what I need, do the processing, put it all the places it needs to go, and then just do that over and over again using the same code every time.
That is cool. So you're using patterns related to immutable data structures and CRDTs, as we're going to get to, in order to add some capabilities to software that was not written with the idea of immutability in mind. Exactly.
They never had this in mind when they made some of this stuff, right? And it's like, and the funny thing is the software's not bad, right? Because it's usually the edge cases. I look at it as like anytime you save something, that's your potential bug, right?
Yeah.
So if you have a known good working configuration, and it's like you just know it's going to work, all the dependencies match, it's like, what's the concern here? And it's like even code that's like got vulnerabilities, it's not actually the end of the world, because it's like, okay, well, why don't you just remove network access for that particular piece of code, right? Because then you get rid of like most of the surface areas. Like you'll find companies where it's like they've got industrial, because I have a manufacturing background, right? That's why I started a career. And you'll find companies, they'll have like, literally a 30-year-old machine that's still running some piece of equipment, because like, okay, that was multiple $1 million pieces of equipment when it was new.
Right.
They're not going to just like rewrite the software just for fun, right?
Right. Yeah, that would be a huge
like,
disruption.
We have to buy another couple $1 million machine for what's the benefit here? Oh, a little bit of perceived security. It's like, no, you can just take that thing offline, and so there's a lot of stuff that just still runs that way, and it's like, I imagine that as we go forward with all the stuff that people are building now and all the technical debt, especially around AI, it's like, okay, how do we virtualize this, remove it from the network, and that way you could still use it even if it has a known vulnerability. It's just that's been mitigated.
Yeah. So we know that there's some bad code in here, but we've
already thought about
its capability of communicating with the outside world or saving anything locally, because we've got those 2 channels, and we can just lock them down. That is a really cool application of immutability. So I've I've approached it from the perspective of let's throw everything away and let's reimagine what would application development look like if we thought about this from the beginning. But this
Mine's
is
the
a really
opposite. It's
practical
basically like,
approach. Yeah,
let's just keep what worked,
yeah,
literally what worked, and don't change it.
yeah. Yeah, and
So,
so you've got the advantages of virtualization, which we had with virtual machines. It's like, okay, that hardware could die, but we can clone that hardware into a virtual machine, and we can get at that. But then, with containerization, then we got some additional benefits. But now here you're building on top of virtualization and containerization, and and getting getting more security, getting more resiliency, and so then the next thing that you sent me some information about was that now you can take these disk images and you can synchronize them across machines.
yes. Okay. So I'm not quite there yet.
Okay.
That problem, distributed computing is just hard.
Yeah.
So
I think that's
I think
from
how I
the book
yeah.
here.
I've got a number of books. Maybe I don't have the right books. I don't have enough books. I've got books.
None of those make it easy. What's going on here?
Who would have guessed? Yeah.
Yeah.
It's hard for everybody except for Michael.
No, it's hard for me too. it's
Yeah.
just hard.
So that's when I reached out to you. So I have these other pieces that have been in place for a while, right?
Mhm.
I've been running some of them. Basically, that wrapper for QEMU I've been running for probably about a year and a half, right? The scheduling component that's basically been improving for the last 6 months, and I've now had it running for basically a quarter. I haven't changed it. I haven't shut anything down. I haven't restarted anything. It just works. The same thing with that DAG processor. So I'm like, great, this is cool. I just need to be able to have this now on multiple machines. And how do I coordinate those machines so at any given time, only one's doing the work, right? And that they can share what they need to share, because obviously it's not going to work if you go to boot a disk image and it's not there.
Yeah.
Right. So
Yeah.
that's the part that I'm working on now. Is like, okay, how can I do this in a practical way? Because Kubernetes is lovely, but once you drop below a certain number of nodes, it doesn't work. Well, not everyone needs hyperscale. Like, most people don't. But most people would like to be able to, like, okay, I have a couple different computers that may be on or off at different times. I'd like to make sure that when they're up, that they're basically backing each other up. And then when they're down, it doesn't, break those processes. You don't want it to just go down because they can't talk to each other. So I played with Kubernetes a lot. I just my initial response is like, the complexity here is just too much for the problem that we're solving, like most of the world's solving. So played with that, and then I took a look at the underlying, like, it's all built on etcd, which is a library that implements Raft. And I'm like, okay, basically it seems like most of the problems, or they're not problems because it works, but the limitations seem to be from etcd, right? Where that seems to be where it's like, if you have not enough nodes, it doesn't work anymore. So I'm like, okay, maybe that's just not the right path. So, that's kind of why I reached out to you, because I'm like, okay, I think I need the CRDT. I need the conflict-free replicated data type, and I need to be able to pass that between those computers. And obviously I need encryption and the keys. So I've got all those pieces in place. My first attempt at running this thing with 3 nodes, it ran for about 3.5 days before the data set, the configuration, the state just vanished.
Oh.
So, because it basically what it was doing, it was passing that state around, right? And I don't know if it was probably a bug in my code, just a guess. But it just lost the state and basically became an empty object. And at that point, it had no idea how to coordinate itself anymore.
Okay.
But basically, that's the last step. Is okay. now that I got these other pieces in place, how do I get this in place? And what I'd really love to do is, do either of you use Linux, either part-time or full-time?
I deploy all of my stuff to Linux, and then when I'm on Windows, I use WSL, and when I'm on Mac, I pretend that it's Linux.
What I'd like to do is basically I want to have like any application that I write, because typically I just write Python programs to assist in my day-to-day. What was the idea for this is I want to basically just synchronize all those in a user program folder, right?
Mm-hmm.
So it's like I can edit it on one, and then it automatically just deploys,
Yeah.
right? Because it's like I guess I could go through like packaging it to PyPy or somehow rolling my own repo, but at a certain point it's just a file.
Yeah.
Can I just synchronize the file?
Yeah. Can we? Is it rsync? Is that the like the operating system command to just say this folder to this folder, just go?
Yeah.
And
Except give me
like,
that peer-to-peer
Yeah.
where it can figure out who's got the newest one and automatically propagate out.
Uh-huh.
So
Yeah, and do it well well enough that that you can have confidence it's going to work every time.
yeah, and basically you could, if you could run a business on it, I could run my life on it.
Mm-hmm. Yeah.
Matt, do I understand well that actually you want to have, for example, 2 or 3 machines which are all the time completely in sync? So you do something on one machine, the other machines are in the same state. And so if you would shut down the first machine, the other 2 machines continue doing what the first machine was doing.
Correct. I imagine 2 pieces to this. One would be the syncing of the files. The other would be coordinating. There used to be a concept of this. I think it was in like the late 90s in the high performance computing space when like we just didn't have the insane single chip massive SoCs we have today, where they actually had operating systems like Linux derivatives that would exactly do that, share state. But I imagine that you can like live migrate the processes, right? Figure out who's running what process. For start, I would just like to know like, okay, I have this desired state that this schedule task is running somewhere. If not, I have a problem.
Mm-hmm.
And then synchronize a set of files so that it has the resources to run those things.
Yeah, and not only this task is running somewhere, but also this task is only running one place.
Correct. Yeah. And I'm cool with eventually consistent. You know, I'm not expecting miracles here, right?
Uh-huh.
But yeah. So, and this would work because everything I'm doing is like you're not changing that disk image all the time.
Yeah. Yeah.
Right.
So it's like changing slowly.
It's not a problem because it's slow changing enough that they will get consistent.
Yeah.
And then when it does get consistent, so what I did, because obviously disk images can be pretty large, right, depending on what's installed. So I basically wrote it. I'm using Flask, and then Waitress is my WSGI gateway, and so there's a REST service running locally on the node, right? And then there's a process that handles broadcasting out the state, and then also the process to detect that the files have changed, and then basically it would get chunks of the file because obviously the file date will change, but then you got to figure out. I don't want to move the whole file every time.
Yeah.
Right. That's a problem. So basically I break it into chunks and then I check some of those chunks and then I can detect, okay, these chunks changed. And then you can just transfer the changed chunks to that other machine.
Yeah. Yeah. Which
is perfect when your underlying thing you're moving is disk images, which most of it doesn't change.
Yeah. Well, you're capturing the individual block write operations. So had you considered moving those operations rather than the resulting chunks?
I think it would be possible.
That would be.
I don't know how I can't maintain that solution on my own. Right? Because I think there is a Linux project for replicated block devices. But once again, I don't think that also fits with my goal of it being eventually consistent, and you can have those peers just turn off.
Mm-hmm.
Yeah. And I don't know that my performance needs, like, if I'm doing this right, like the goal for any great code should be like, you write it once and you run it forever.
Yeah.
Yeah.
Yeah. Yeah. So
You know,
once you found the
hardware
bugs,
people, will be like, well, your code's old anytime you need to change hardware. But I'm like, no. That's actually a job. That's actually your job to solve that problem for us.
Yeah.
So we don't have to keep doing it.
Yeah. Okay. So yeah. I think one of the key things that makes this work is that the disk image is not the database. It's not the volume. So you still mount a volume, and you still use that for managing application data, the things that change quickly. This is things that change very slowly.
And well, in my case, right, for my use cases, I don't store any application data.
Mm-hmm.
Right? So like nothing actually gets stored to the disk. I use other applications in my, the way I like to think of my role is I'm like FedEx. You don't typically ask FedEx to store your stuff.
Yeah.
But they do move it, right?
Yeah.
So I'm doing my role right if I never have to store your data. I just move it from one place to another, right? And then I could be connecting to a database. I could be connecting to an application. It could be REST APIs. Well, who knows? It doesn't really matter. But in all practical case, I have to write, and this works because I wrote that code in such a way where it's like you can run it. You could run the business operation. You could run it again, and it doesn't destroy any output, right? It's safe to do that multiple times. It's that message structure where it's like, I could see the message multiple times, doesn't break anything.
Nice. Yeah, make it idempotent. Yeah. Okay. So I want to kind of go back and fill in some of the gaps. So you'd mentioned etcd using the Raft protocol or algorithm, and then you'd mentioned CRDTs. So I want to kind of fill in the gaps about. You'd sent me some information about etcd and Raft, and so I was able to study up on it. But for for everyone else, can you give us kind of an overview of the Raft algorithm? Maybe not go into the details of exactly how it works, but why does it exist?
See, this is where I'm not actually that academic.
Oh, okay.
Right. Like at the end of the day, like, I get paid to write software that works.
Yeah.
And preferably the longer it works, the better.
Okay.
Because I don't want to be in there every day.
Yeah.
But basically, it is a form of eventual consistency. And it's basically, it's like a very complicated key store, right? So it's almost like a database that you can pass kind of object data between the different systems. In theory, it would work awesome for my use case. I'm just not sure how to get to here from there because underlying, like, I'm sure someone, because I'm mostly Python and etcd is written in Go. And I can't get to here from there. In terms of like hacking that up, because it's on GitHub. I guess if I had the skill set too, I could hack that up. Basically be like, how could I make this where it doesn't store anything to the disk, it's immutable, the peer communication, all that stuff. I think it would be possible to change it that way. I'm just not sure how to get from here to there. So I'm like, okay, I'll try my own. And that's where I'm like, okay, I need to learn about these conflict-free replicated data types. So I think I picked it was like LWWN, the last write wins. I think so. Yeah, last write wins. Yeah.
Okay. Yeah. So okay. So I'll see if I can kind of fill in what. So the Raft algorithm, as I understand it, it is an evolution of the Paxos algorithm that's designed to be easier to explain, easier to understand, easier to to validate. And just like Paxos, it has undergone the scrutiny of using TLA plus to make sure that the algorithm as specified is correct. and produces the desired results. And basically, it's a consensus algorithm. The various nodes in the system will send messages to one another, first to elect a a leader, and then for that leader to gather consensus from the other nodes as state changes, and then notify the other nodes. So yeah, there's a lot of overhead and a lot of messages flowing back and forth in order to achieve that kind of eventual consistency. And that's the kind of.
But I do need it, because basically what's missing is I don't have a leader. I'll be able to get the files, and I was able to do that for multiple days. I was able to move 100 gigabyte files back and forth, sync the changes, no problem. There's no leader though, right? So if I want to implement the scheduler, I need a leader, because you got to have. And I don't know if that's where this thing falls apart, and that's why you can only have like one node, right? It is a hard problem to solve, right? I'm not academic to understand all the pieces of it, but it's like, okay, yes, how do you confirm that when these nodes, they may still be online, but they can't talk to each other? How do you confirm you only have one leader? That's a hard problem.
Yeah.
So
yes,
maybe there's a way where we just, use cloud for what it's really good at, where you have a bare minimum of where it's like you can just count on the cloud to coordinate who's there. That could possibly do it, right? Because it's not like if that went down, everything else goes down anyway. So
yeah. So I think I think actually I misspoke just a moment ago when I said when I said eventual consistency. What Paxos and Raft guarantee are strong consistency. So at some certain time, that everybody has the same state, and so there's got to be a lot of negotiation to reach that point. CRDTs give you a weaker guarantee. So it's not strong consistency; it's strong eventual consistency. The weakest guarantee, just eventual consistency, would be that if you were to take a look at it at some point in the past, then you could say that everybody has eventually achieved the same results, but you can't say that at this particular point in time I know that they're consistent. That's strong consistency. Strong eventual consistency is in the middle, where what we're after is eventual consistency, but we want that with the minimum number of communications. We don't want any further negotiation. We just want to, as soon as everybody has heard the updates, they all compute the same state. And so strong eventual consistency can be leaderless, whereas strong consistency has to have a leader, or at least.
And then I think
so.
you mentioned in the book, right? It's like at a certain point, your applications have to be designed to work with this. You can't just take an application that's insanely stateful and say, I want to run it this way.
Yeah.
Right. So you have to basically write it with this in mind, because it's like, I might not even care that it runs at two places at the same time every once in a while, if certain conditions are met, in that, maybe what it does is it goes, wakes up, checks a message queue, checks that message out of the message queue, does the processing, right? Because that message queue now isn't going to give that message off to the other node, right? So that problem goes away. But there are some cases where it's like you might not want it running, particularly like applications where you can't control like how it handles its API rate limits and that sort of stuff, where it's just, okay, well, I'm not doing this. So, but yeah, you have to fundamentally change the architecture a little bit to do this. But once you do it, it's like, there's no way I'd be going back to writing anything I do in any production sense any other way. Because it's, I could consistently count on every time it boots up. It's like the first time I set that thing up, all my dependencies are there. Nothing on the disk got modified. Nothing extra got installed. No one installed anything. And as an added bonus, I can basically, take a checksum of, just like the Docker images, right? When you actually stuff everything in it, you have a checksum to validate, okay, this code is the same as what I executed before.
Yeah. Yeah, and so if things go wrong before you get to the point of committing your change, then you still have the old image.
Yep.
So there's
the
it's
analogy,
non-destructive.
I gave a demo, right, to some other engineers, and I was screen sharing it, and I'm like, I booted up a Ubuntu VM, right, and I did a sudo rm rf on the root directory, and then obviously you can't even do that, so you have to add no preserve root, and then I fire this thing off, and you're literally watching the desktop like fall apart in front of your eyes, because it's like, all the desktop icons get deleted, the desktop wallpaper gets deleted, all the configs for your menus and stuff just get deleted, all the icons. So basically you're left with a computer, you can't even shut it off because you can't access like the terminal or the shutdown menu, right? Because none of that exists. So I just close the VM. It asked me to save. I hit no, and then I boot the thing back up, and it's exactly where it was.
Yeah.
Right. So it's like, that's like, if we want to move forward with computing, that's what we're going to do. It's like, imagine if your computer had a save button, right? Like in a practical sense, if your computer had a save button, would you use it differently? And chances are you probably would.
Yeah, now I'm curious about your implementation so far. If you had pushed save, would you still be able to get back to the old image?
No.
Oh, okay.
No, not yet.
But that would be, I imagine that would be possible if that was something that you wanted to go for.
And so like the Windows recall, right? People are talking a lot about this. It's like, other than the fact it's insanely creepy in the implementation of the way they did it, the concept is actually really great, because I want that for the type of workloads I do, right? Because if I combined capturing the video, because basically I actually boot a real VM that's got a real virtualized desktop, and it boots and it starts a terminal and it runs commands and there's output from those commands. I don't want to implement an entire logging framework. If I could just record what happened, store it with it, package that up, now I have basically, I know where it connected to, and I have a full screen capture of everything it did. That would be great in an enterprise sense, right?
Yeah. So it's just a matter of
their market was wrong. Like, let's go after the users. They won't find this creepy at all. So here we are. But
but security people, absolutely. Let's do that.
Yeah.
Except we're not sending it to you. I want it. That's the difference in security.
The Kemia project, very interesting. I think that one of the last obstacles, because I think that the future of computing really is like virtualization. Like you can't continue to have these big architecture changes in hardware without at some point, like you just gotta commoditize the compute within the compute and call it a day. So I think that's the kind of the final frontier. But what's stopping all this from going where it really needs to go is the video. How do you accelerate the video in that virtual machine in a open and standardized fashion? And they've been talking about it for like 8 years. And like Red Hat's done talks on this, and they've done demos, and there's even a SRIOV virtual functions. It exists, it's been done, but they still see it as a enterprise feature. But it's like, if you want to sell consumers this absolutely insanely powerful hardware, okay, at a certain point, what's the goal here? Everyone's going to have like 5 4090s, at home. Like, no, like this isn't going to happen. I don't get, like, I'll buy a bigger GPU if I can split it up, and if I can split it up where I'm not like, okay, we talk a lot about zero trust. It's like, well, I have to trust NVIDIA.
Yeah. Yeah, true.
It's not exactly zero trust, right? So I have to trust NVIDIA now. How can we do this cross architecture, right? And I'm not asking them to like open up CUDA. It's like, no, can we at least get some basic video acceleration, 3D acceleration, and then like the video codecs for the hardware accelerated encoding and decoding to make like these virtual terminals practical. And I'm just curious. I think it's going to be interesting to see which vendor gets there first, because Intel has been like hit or miss on this. I have a card. I have an AMD card that's like almost a decade old now that could do this. But, no kernel driver support anymore, right? So Fire Pro, this is one of the first cards where you could, in a virtual machine, chunk off a little part of it and say, hey, you got this is acceleration in your virtual machine.
Yeah, you would think
why
that would be...
Why 8 years later do we not have this? Oh, wait, because it doesn't help you sell more shovels in the AI rush. Right. So.
Interesting. Yeah, okay. So, so the solution that you're implementing for synchronizing these images is you're building this on top of a set based CRDT that you so this is a Python CRDT library. I happen to have it open here.
And I only actually needed one part of it, right? Because I'm trying to do this in such a way where I don't want to have to install extra libraries.
Yeah.
So like less really is more in terms of the code. And I don't know that this is the right implementation at all, but basically I know this part's right. So I've got 128-bit AES encryption of basically the raw HTML body that gets passed back and forth between these for all the messages. And it's shared key encryption. So at least you get that component. Obviously, I think as that scales, that's a different problem to solve, that you probably want to be able to like revoke nodes and do that sort of thing. But for my personal use case, I think this is perfectly reasonable. And then I don't think this is right either, but just to hack something together to get it running is I was pickling the Python object, right?
I'm familiar with that term.
You're basically converting the object in Python memory to bytes that can then be loaded on another system.
Oh, okay.
Yeah.
Oh, that sounds very powerful.
It is very powerful and also very dangerous if you don't use it in the context of encryption. Because it allows like arbitrary remote code execution. So that's why a lot of this stuff is a little early in its piece, but it's like I'm a one-person team. I'm working at a company where I have to maintain the business, right? Keep a business running. So it's like I do what I can. This is kind of that experimentation piece, right? So I got the other pieces working. Those are basically in production now. It's how do I finish this one? What's the best implementation? And
yeah. Okay. So looking at this is the Python 3 CRDT. And so one of the components is the last writer wins element sets. Is that the one that you were talking about?
Yep.
Yeah. So so this is a set. You can add. You can and this one. It's got two sets. It's got an add set and it's got a remove set. But you've also got a timestamp in the remove set.
Correct. Yes, and that's what makes the whole thing work. Because, how do you remove something and then have it not keep adding itself back from a node that hasn't communicated in a while?
Which is an issue that I talk about repeatedly when talking about the delete restore pattern in historical modeling. Is that if you want to be able to delete, restore, and then delete again, you have to have a timestamp.
Which is foreign to most software engineers typically designing a data structure for storing that, because it'd just be a Boolean. Sometimes they just remove the record, maybe if you're lucky, they put a Boolean on it to do a soft delete.
Mm-hmm. Yeah, but that's still not enough information to be able to do the merge. So
Yeah.
the thing that makes a CRDT work is that it is a forward-only data structure. So it moves forward in some dimension. You get to define what that dimension is, give it a greater than operator. And so you say every time I perform an operation, the new one is greater than the old one. And that is a partial order. So that means that somebody else could be moving forward in that same dimension, but differently. And then when you merge, you're computing the least upper bound. You've gone forward from both replicas. And so, yeah, if you are able to set a flag, remove a flag, you're going back to a previous state, and CRDTs don't allow that. So yeah, instead, under the covers, it's got two sets, and it looks from the outside as if it's just one set. But the two sets, keep track of, these are all the things that I inserted, and then these are all the things that I removed. And if it's just that, then it's the two-phase set, which allows removal but not reinsertion.
When you go to use it, you calculate it.
Mm-hmm.
And it's, because like you said, it has to be invisible to the use. Otherwise, it's like, okay, now I just have a whole bunch of extra complexity I'm using.
Mm-hmm.
No, but it's like you just create an object. That object underneath its sheets, it's got all the things it needs to keep track of that state.
Mm-hmm.
And then when you need to access the state, you just basically got a couple methods on it to add, remove, merge, and then one for like display, like give me the current state.
Mm-hmm. Yeah, nice. And so by going to this last writer wins one, now you do have the ability to remove and then re-add, because that removal has a timestamp associated with it, and so it's that particular removal that has been that took effect. But so now applying it to the disk images. So I think that but the thing that makes this a good fit for your use case is the fact that one, you expect it to be running on just one machine at a time, and two, it's a slow operation. It's not the application data. It's operating system configuration.
And typically the changes to the disk image are only made by an actual person in front of a terminal.
Yeah, that's a key one. Yes.
Right. I can only be in one place at one time.
Yeah.
So that's an extra benefit. And even if you're dealing with other people, at a certain point, like, I don't know how big of a team you would actually need to maintain an operating system with all your things for a business.
Mm-hmm.
Right? I don't think that's a huge team.
Yeah. And so, things, consensus algorithms like Paxos or Raft are there to guarantee that you're not going to get these concurrent edits, or if you do, then that one has been rejected. It's like, I'm attempting to do this. Let me talk with everybody, and then you get back, nope, you can't do this. Versus with the CRDT, go ahead and put it in there, but then when it merges, you might find that that your change didn't have the effect that you expected it to. So in this case,
or someone else modified it after me, and it's like, well, actually, I do want the last one to win, but it just means your team needs to communicate more.
Yeah.
Yeah.
And if you provide the visibility, actually, I don't think this particular CRDT. Yeah, I don't think this particular CRDT provides the visibility that you would need for the CRDT itself to facilitate that communication. So, if you think about Git does have this visibility. It facilitates communication. If you've got concurrent edits, there are two branches, and you talk to you can see the developer's name right there in the commit history. You have that conversation.
And there's no reason this wouldn't be complementary, because it's like at a certain point you could just have a job to run the Git polls on all the machines, or event triggered, right, to push it there, and it's like you've got all those pieces in place to keep track of the scheduling and that sort of thing. Yeah.
So I think this Yeah, I think this satisfies your use case in that it's yeah, most of the time you're not going to have these concurrent edits. When you do, it's going to pick one and it's going to continue to work consistently, um, and then it's also that you don't really have to think about it too much. You know when you're moving from one to the other. Yeah, I just did this, and now I'm over here, and you can kind of spot check real quick. Yeah, is the change that I intended in this
Yeah, or even if you have a
in this
couple
new image.
person team, you're just like, hey, I'm
Mm-hmm.
updating, these couple applications, right,
Mm-hmm.
from their apt repos or whatever, and be like, I'm gonna push that change after I run the unit tests, and you know,
Mm-hmm.
yeah. So
Yeah. Cool. Yeah. So, um, yeah, I'm always happy to see people going back to the mathematics and saying we're going to apply this. We know its strengths, its limitations, its boundaries, uh, and so we're going to apply this to solve a real problem, as opposed
well,
to
I mean, the alternative
yeah,
is we built, the software industry has built a massive pile of complexity,
yep,
and then the solution's like, well, let's throw some AI on top of it, which is more complexity, in hopes that this is going to make it better.
yeah,
And I'm looking at this and like, why?
mm-hmm.
It's like, I get it. It keeps a lot of software engineers employed. We can just keep writing code in circles, but like we have some stuff that works. Why don't we keep that? Why don't we advance the industry, not kind of just move backwards?
Mm-hmm.
So,
That is awesome. All right, we are getting close to the end of the hour. Any final thoughts? Cool. Well, yeah. Thanks, Matt, for hanging out for this hour and sharing what you've been working on. I would like to hear how how this progresses, how you're able to get this working, especially because yeah, I'm imagining that this library was tested with small data structures, and here you've got disk images. Um, so yeah, I'd
yes.
be really excited to hear
Um,
how it scales.
just for any of the viewers, anyone seeing this, what I'd like to ultimately do with this is I'd like to basically package this in a GNU distribution, right? Because I kind of see the workstation computer, the server, the client all converging into one in the future. And it's like, can we just give the workstation the pieces? And I think these are some of the pieces to put that together in a way where it's like, okay, I can run it like it's a server because I get that resiliency across the different systems.
Mm,
I still have the desktop user interface and all that sort of piece. But I don't want to do this if I can't put it into infrastructure that people can own,
yeah.
right? Because like, why are we in such a mess now? It's because everyone's renting software.
Mm,
So can we save this set? Because I think this is going to be a powerful tool set. Can we add this to the GNU ecosystem, the FOSS ecosystem? So it's like we can actually build software that can still be running 50 years from now, right? 25, 100 years from now. Because it's like there are use cases for software to run that long.
mm-hmm.
Um, I could think of one thing: banking, right? High risk, going fast and breaking things when you're now dealing with people's life savings, probably not the best idea.
Yeah.
So it's like, how do we do this? How do we do some of these things so we can have that long running software as that world of hardware continues to move around it? You build a little capsule, be like, cool. Like, that was the goal of virtualization, right? But it's like, we all kind of have to be on board with it. And then that software license ecosystem has to support being able to do this where, how do you keep an old game server from like something 20 years ago that maybe there's just a few users, but it's like, it's now part of internet history. How do you keep that alive,
Mm-hmm.
right? When now there's not necessarily there's no business model around this. No one's
Right.
going to, who's going to have the one person business? And even if you did, you wouldn't want to do it because when that person's gone, right? So that's in terms of preservation, it's like, how do we do this? And I think that's why I haven't released any code for it, because it has to be in the context of like, I need this to be part of a distribution to give us that whole GNU tool set so you can actually use this thing, not just the, you know, the tools that I built on top of it.
Excellent. Yeah, I love that vision. Yeah, if there's anything I can do to help with that vision, then yeah, thanks for reaching out, and please continue to run things by me.
Awesome. Yeah, thank you so much. It's been great chatting with you guys.
Yeah.
All right.
Running old software is something that interests me.
Yes, that is Jan's entire business.
As the new stuff continues to get worse, I'm like, okay.
No, but as you said, I still have software which I developed in 1999, which is still running at my customers. But at a certain moment, you get trouble with compatibility with new systems, with security. So it is indeed a problem,
Yeah.
and I'm very interesting to see a solution to that.
Yeah, I think that there's some work that needs to happen on QEMU too, where it's like, I want VLANs, I want user LAN networking with VLANs, and I want a firewall for it. If we can get all those things plus the screen recording, beautiful. Put all this stuff together, and now you could basically run that software with like, it can access these places, it can do these things, I'm gonna record what it did, and I'm gonna run it every couple, whatever interval. And you'll have all the tool set to do that. And it's like, it doesn't really matter what vulnerabilities it has. Cocoon that thing up, launch out in the world, just let it run forever. So.
Yeah.
Awesome.
All right.
Well, thank you so much, gentlemen.
Thank you.
Yeah.
Have a good one.
Have a great week.
Thank you very much. See you next week, I think, Michael. Normally, I should be there. If there is something in between, I'll let you know. But the week after that, I will definitely not be there.
All right.
Next week, probably yes.
All right.
I think
Sounds
so.
good.
I hope so. Okay, Michael. Thank you very much.
Right.
See you.
Thanks, Jan.
Bye-bye.
Bye.